Okay, thanks very much. So yeah, I will indeed carry on with discussions of the colored vertex models. So in the previous lecture and also in a little bit of the problem session from yesterday, I basically been outlining the basic properties of these models, in particular the stochasticity of the model, the color blindness property of the model, and also the fact that the model is integrable, satisfies Yang-Baxter and unitarity equations. And so now we're basically done with all of the machinery that we need. I'm going to progress towards defining certain types of partition functions that give rise to families of orthogonal rational functions. So we're going to need a small definition throughout the course of the lecture. So I'll just do that pretty quickly. So let's say definition number one. So I'll be using strict compositions to index the functions that I look at. So a strict composition, usually denoted with mu, consisting of n parts. And this little n here will be exactly the same little n that we have in our model. So strict composition mu1 up to mu n, which lives in Cartesian product of positive integers n times. So this is just an n tuple or an n vector of positive integers mu I, such that mu I is not equal to mu j for all I not equal to j. So it's just basically tuples of positive integers that have a pairwise distinct property. All right, so given a strict composition, we will want to have a way to map it to what I'll call a string. So given a strict composition mu, I will define S of mu. And so S of mu is going to be actually a vector that's sort of infinite in one direction. So I can write this as S1, S2, S3, and it continues on indefinitely. And so this will be defined in the following way. So basically, if I look at one of these components of this vector, in particular the mu kth component, this will be set equal to k. So that's going to hold for all k from 1 up to n. And otherwise, so if I look at a component that doesn't correspond with a part of the composition, then I will just set that entry equal to 0. So maybe this is more clearly illustrated on an example. So let's suppose we have the following strict composition. So it can be 3, 1, 7, 6, 2. Okay, so this is an example where little n is equal to 5. And in this case, the corresponding string will just be the following. S mu in this case will be 2, 5, 1, 0, 0, 4, 3, and then trailing off in an infinite string of zeros. So what is actually happening here? So basically, you can think of this first vector, so the strict composition, these are going to be something like the coordinates of some colored particles. So I'll just write here coordinates of colors. Okay, so what does it mean? So it means that the coordinate of color number 1 is the first entry here. And so indeed now if I look at the corresponding string here, color number 1 indeed sits at coordinate number 3 inside of this string. And likewise for the second one, this is going to be the coordinate of color number 2. And in this case, it's positioned at location number 1. Okay, so out of doing this, you're always going to get a string of this form where each of the colors, 1 up to n, appears exactly once. And everything in between will just be zeros. So we're basically going to, toggle between the two of these when we actually define the functions that are of interest to us. Okay. So hopefully that's clear. If it's not clear, please ask now because I'll be using this throughout the whole lecture. So, okay. So let's come now to the definition of the first family.
A composition, usually you are interested in the sum. Are you also interested in the sum here of the numbers?
Yeah, you can think of so indeed, if I look at the sum of these mu i's. So this is I want to say this is a quantity that in some way keeps track of the weight of the partition functions that we look at. So there is a notion of weight, but it's a little bit more complicated because the functions we're going to get are going to be rational functions. So a priori, keeping track of the weight doesn't really make as much sense as it would say with polynomials. But indeed, this is a kind of somehow this quantity here is telling you how big the function is or how far the particles have moved. Something like this, yes. All right. So, okay, definition number 2. So this is going to be the first family of functions that we're interested in. So let's set it up. So I'll fix, as usual, integer little n and a strict composition. Mu, which is mu1 up to mu n. And let S mu be the associated string. Okay, so with all of that, we then define the following function. So it'll be denoted little f sub mu, so that's the strict composition. And it will depend on an alphabet x1 up to xn. These are going to be spectral parameters of our model. And actually, even though it will not be present in the notation, the function depends on a second alphabet. It's something like the horizontal and the vertical variables of the lattice. But in practice, we're not going to care too much about this secondary alphabet. So we'll suppress it from the notation. And so this is the definition now. So I'm going to have a lattice. And I think maybe I should have already drawn this. So I'll draw it and then make a copy. Okay, so here we have it. And let me just copy that now so that we have it for later on. All right. So what's going on here? So I need to assign some spectral parameters and boundary conditions to this thing. So let's do the spectral parameters first. So the x's are going to enter via the n rows in horizontal rows of this lattice. So x1, x2, up to xn. And then there's going to be, as I said, a secondary alphabet of y's, y1, y2, and so on. But we're not going to care too much about those in what follows. And so now let's set up the actual boundary conditions. So we're going to take all of the incoming colors along the bottom to be equal to 0. And likewise, all of the outgoing colors on the right of the lattice will also be equal to 0. And then all of the interesting stuff happens on the left and on the top. So on the left, I'm going to take the first edge to be color 1, second edge to be color 2, and all the way up to the nth edge. And then at the top, I have the string. So this is S1, S2, S3, and so on. So what you should think of happening here is that you have color 1, which enters the lattice via this edge here. And color 1 is going to make its way through the lattice. And ultimately, it's going to leave the lattice at some position up here. And the position where it leaves is exactly going to have coordinate mu1. Okay, so this mu here is mu1 up to mu(n). So the coordinate where color number 1 leaves is precisely mu1. So I know I've written it in terms of these s's here, but that's basically what the s's are doing. And so you do the same for each of the n colors. Okay, so that's our first function. And just in case there's any confusion about whether you can really think of this thing as being a permutation graph, clearly I could have also just drawn it a little bit differently, something like this. Where here I take, let's say, 1 up to n, and these are zeros. And then here I have some zeros. And then here is my string S1, S2, and so on. Okay, so definitely it's in the same family of objects that we've been studying so far. But I suppose one thing that is a little bit different, and it's important to remark about this, is that strictly speaking, this quantity I've defined here, it lives on a semi-infinite lattice. So actually, these horizontal lines, you should think of them as extending all the way out to infinity. And the reason why this quantity continues to be meaningful is that sufficiently far to the right, this string is going to terminate just in zeros. And so whenever that happens, you're going to have at some point nothing but edges that are decorated with zeros, which means that at some point the lattice will just freeze into a product of vertices of this form. And we know that this vertex has the weight 1. So indeed, this object is meaningful. We can define it on a finite lattice, but we can also extend it to live on an unbounded lattice in view of this property here. Okay. Are there any questions about the definition of this function? Okay. So this function is going to have a companion, which will be denoted little g. And actually, I guess the setup of the definition is exactly the same. So I'm going to, I should not do that because then I will lose the, let me first paste the, I'll just write it, the definition 3. So with the same setup as the previous definition. We define a second family of functions. And so that's going to look like this. So G mu, again, I have my primary alphabet x1 up to xn. And the setup is a little bit different now. So actually, the horizontal lines are going to be oriented in the opposite direction. So like this. And the boundary conditions will look like this now. So I still have zeros all the way at the right edge. Now along the top, I have nothing but zeros. And what changes is that the string now lives along the bottom of the ladder. So S1, S2, S3, and so on. And along here, I still have color 1 exiting via the first row, color 2 exiting via the second, all the way up to the nth. And in terms of the spectral parameters, this will still be Y1, Y2, Y3. And for convenience, because it makes the formulas ultimately look a little bit nicer, I'll actually choose the horizontal parameters to be U inverse, X1 inverse, all the way up to Q inverse, Xn inverse. It's a bit more tricky to write it down, but it will ultimately make some of our formulas a lot more elegant to do this. All right. So this is the second family of functions. So let's maybe just make some remarks about these. So both f mu and g mu define a family of multivariate rational functions in their variables. So in x1 up to xn, and also in the y's. However, and important to note, but note, they are not symmetric functions. Actually, in either alphabet. But in particular, they're not symmetric in x1 up to xn. Okay. So we're going to see a lot more about these functions and why it's interesting to consider them in the first place. But before I do that, I wanted to find one more function, which is also going to play a role in what we do. And unlike the previous two, this one is actually going to be a symmetric function. So the setup is very similar. So again, fix an integer n greater than or equal to 1. And now we're going to have two strict compositions. Which I can write mu1 up to mu(n) as previously, and the second one I'll use nu as the letter. And in a similar vein to previously, I'll let s mu, the s1, s2, this is the string that is associated to mu, and I'll let s nu be written as t1, t2, etc. So these are going to be the associated strings. Okay, so this time definition looks a little bit different. So again, we have our lattice, but the boundary conditions are going to look very different this time. So I'm going to instead I still have string S living along the top of the lattice, but now I'll have another string, which is the new string, which lives along the bottom. And along the sides, I have just zeros now. Okay. And in a similar vein to previously, I'll still use y's for the vertical spectral parameters and x's for the horizontal ones. But something changes here as well, which is that the number of horizontal parameters that I have is now going to be written as capital M. And I do that to indicate that this number of rows that you have here is absolutely not related now to the number of parts that the composition has. So you can take, in particular, you could take something like 100 rows or however many you want, whereas n could remain very small. All right, so that's going to be our function. And I will write that as capital G of mu over nu. So you can think of it as a kind of skew function in x1 up to xm. Okay. And so what's going on this time is that all of the colors are entering via the base of the lattice and making their way up to the top. All right, so somewhere at the base of the lattice, I have color number 1. Let's suppose it enters here, and it's going to make its way through the lattice and exit at some position. So the position where it comes in is nu1, and the position where it leaves is mu1. And similarly for each of the n colors. Okay. So unlike the previous two, well, this function is symmetric in its first alphabet, x1 up to xm. So the proof of the symmetry, I'll leave it as an exercise for those who maybe have not seen this before. It's a very standard proof. So basically, the idea is to use the Yang-Baxter equation. And basically, I'm going to insert a vertex at one of the edges of the lattice. It doesn't really matter which one. And the claim is that I can insert such a vertex for free because of the fact that the boundary conditions that I have here are all zeros. So I can basically attach a vertex that has 2 zeros exiting, say. And the claim is that this picture that I've drawn here is equivalent to the first one. And then once I've attached that vertex, I can then use the Yang-Baxter equation to start to transfer the vertex all the way through until it ultimately comes out by the left edge, and then I can delete it via the similar argument that allowed me to attach it. And so that then proves the symmetry in the two x variables that actually participate. So yeah, if you've never seen that before, then that's a nice exercise. All right, so that's all the definitions that we're going to need. So I guess, yeah, if there are any questions at this stage, then please feel free to interject.
Yeah, just one quick question. Could you also explain why this argument fails for f mu and small f mu and small g mu?
Yeah, so we're going to actually see why that happens later in the lecture, but just to give you a kind of preview, let's suppose we want to use the same argument for f.
Right.
So again, I would be able to attach a vertex here, and say a vertex that has all zeros. So this I can do as before. But what changes is when it comes out the left edge, you will then see basically something like this. So suppose I do it on rows I and I plus 1. So I'll have something like this. These will be the colors that I have on those edges. And so when it comes out, the other side, I can see actually now that these edges here are not frozen, right? Precisely because of the fact that these two colors are actually different. Right? You see, in the case of G, I have all zeros here, I have all zeros here. So when that vertex comes through for G, I have two zeros that enter, and that will then force these two edges to be zeros as well. So basically I can detach the vertex because this thing has weight 1. But in the case of F, this is not true. In the case of F, once that vertex comes through, I actually have two possibilities for these dots here. So either it's going to be I plus 1 and I, or the other possibility is that it will be I and I plus 1. So you don't quite get the symmetry. You get this sum over two terms. But we'll say more about that as we go further. All right. Okay, so what to say about these functions? So aside from the algebraic properties that we're going to explore, they do have some probabilistic utility. So I definitely will not be focusing too much on probabilistic aspects in these talks, but it is important to point this out. So both of the functions f mu and g mu over nu have application to integrable probability. And the reason for that is that they satisfy the following properties. So if I take a sum over all strict compositions, mu of the function f mu, this adds up to 1. Provided I work in the regime where all of the vertex weights are, let's say, real and positive. Okay, so that's the first property. And the second property is if I sum, again, over all strict compositions mu, the function g mu over nu, x1 up to xm, this also adds up to 1. And that holds for any fixed nu. All right, so what this means is that you can actually use either of these functions to define some probability distribution on strict compositions. So both functions define probability measures on strict compositions. Okay, and so in terms of the sort of pictures you have here, so the function g, for example, you should think of that as, you have some collection of particles that enter via the base. And what this thing is actually computing for you is the probability that those particles ultimately make their way to the positions at the top after, m applications of these rows. So this is the one way of interpreting what's going on. And likewise for the function f, I have a kind of Markov process in the quadrant. So I have a collection of colors that enter via these edges here. And there's a kind of Markovian procedure that allows you to start from the vertex in the bottom left here. And first of all, you figure out, what is happening with these two edges here. So basically, whether this is going to be a 0 and a 1 or the other way around. So you sample your vertices one by one, basically along these kind of anti-diagonals. And in so doing, you build out a random configuration of colored paths. And so what f mu is computing for you is the probability that after you act with n rows, you'll ultimately land in this state. Okay, so there's some probability underlying these objects. Now, in terms of
sorry, can I?
Yes.
Yes, I'm a bit confused about this point. Could you scroll back up to the f mu, please? So as you're summing over mu, it is not. I mean, it's only the top part that is changing, right? The left is always, the left side is always 1 through n in that order, right? So
that's correct. Yeah.
So there's a kind of double sum. We are summing over all the configurations as well as the boundary conditions on the top, right?
That's correct. Yeah. So if I want to compute f mu, I have to sum over all possible internal configurations. That's true.
Yeah.
In order to actually show that this thing is adding up to 1, I have to then sum over all possible things that happen at the top boundary. Yeah.
Right.
And basically, the proof that this thing adds up to 1 is basically just boiling down to the stochasticity of the underlying model.
Right.
Now, I've stated it here in a form which is a little bit different to what we actually proved, because as I stated, stochasticity, normally you take one of these Z sigmas. So, it's some, whatever it is, some permutation.
Right.
And normally the prescription is that you're supposed to sum over all of these edges along the top in order to see that the thing adds up to 1.
Right.
And so in terms of what we have here, you can see this is not quite what's happening. Like basically, we're summing over all of these edges here. But these ones are kind of just fixed to be equal to 0.
Right.
So the reason why it ends up working is you consider a kind of, let's say, a truncated version of the f here. So basically, I take a string which is finite now, say going from S1 up to, I don't know, SP, for example. Right? So I can see that, okay, I have my colors that are supposed to exit here. But suppose one of the colors actually, decides to migrate all the way across and actually end up going out via one of these edges instead. Right? So there is a total weight associated to this move, which means basically the thing has to step across, basically p times in order to make its way to the right boundary.
Yes.
And every time that happens, it gets a weight. And so you end up multiplying the p of these weights, which are all less than 1, bounded away from 1. So in the limit where p goes to infinity, you can see that these contributions become exponentially small. So basically, you first look at the statement for finite p, and then you show that as p tends to infinity, it's very unfavorable for a path to travel all the way across. This is the reason why we can sort of condition on these things being equal to 0.
I see. So is the point that the same argument will not hold if I like take only finite, let's say P in your notation, many vertical edges? This will not work?
Yeah, so if it's infinite size, I would also need to sum over these edges as well.
Okay.
So I would have to symmetrize over everything. Yeah.
Okay, thanks.
That's correct. Yeah, yeah. Okay. So yeah. So again, this kind of looks maybe a little bit formal. It's not really clear perhaps what is the probabilistic utility of this. But the point is that the model that we're looking at happens to degenerate to a very wide class of stochastic processes that have already been studied at length in the literature. So the degenerations are, I would say, tedious to do. So they require a lot of care and you have to take limits and do things carefully. But all of these degenerations are in some sense known. So as long as you know that the model degenerates to whatever stochastic process you're interested in, you can just work at this highest level, and then whatever formula you get, you can then take appropriate degenerations of it. So maybe I'll just list things that the model actually is known to degenerate to. So there's this stochastic colored vertex model. And so one of the things that you get almost immediately is this degenerates to what's called the multi-species RCEP. I might say a little bit more about that if I have time. But there's also a procedure that you can do on this, which we've sort of hinted at a few times, which is called the fusion procedure. So then you get this kind of fused model. So the model becomes more complicated, has more complicated weights. But on this side, there is actually pretty rich landscape of things happening. And in particular, one sees the appearance of what's called the beta polymers and all of their various degenerations. So there's a pretty rich landscape here, and somehow at the base of all of this landscape, which is quite complicated, I'm not going to sketch it all. There is something called the Ayyer sheet. And so basically everything in this kind of hierarchy ultimately has some kind of limiting point in the Ayyer sheet. And there was actually a pretty recent paper of this is Amal Agarwal, Ivan Cohen, and Milind Hegde. And so in this paper, they actually looked at precise mathematical statements. So they study something which is called the colored height function in the stochastic vertex model. And so that's a sort of discrete random variable that you can associate to your random configurations of paths. And under a certain scaling, which is the so-called KPZ scaling, they actually show that this thing converges to the Ayyer sheet. So that's quite recent. I think basically dating from either earlier this year or maybe end of last year. So anyhow, just to say that there is a pretty rich tapestry of probability going on behind this model. All right. So I think I'll press on with the algebraic properties of these functions. And sort of the next lot of algebraic properties that I want to look at, they're sort of motivated actually by looking at these equations here. So I said that these equations allow you to see that this will define a distribution on this random variable mu. So you might ask, well, if you're actually able to put a distribution, maybe you can also talk about computing averages. So maybe I can compute the average of some observable with respect to this measure. And the following two identities essentially provide an answer to that question. All right, so these are going to be the so-called Cauchy identities. So proposition number one is that the functions g mu over nu and little g mu, they satisfy the following summation identity. So what is it? So it's saying if I take a sum over all strict compositions mu, g mu over nu, in this first alphabet, x1 up to xm, and for the other function g, I'm going to have a clash of notations if I also use x for this. So I'll put z's for these, z1 up to zn. And so the claim is that you can actually do this sum. It's an infinite sum, but it has a very clean answer. So first of all, I obtain a product. I equals 1 up to m, and j equals 1 up to little n. And that's 1 minus q xi zj divided by 1 minus xi zj multiplied by the function g nu in z1 up to z. Okay, so this identity, there's a couple of different ways you can think of it. So if you don't really care about probability, you can just see this as a sort of formal identity of rational functions. So it's holding as a kind of formal power series. But you can also view it as an analytic statement. So if you actually care about, the absolute values of the weights that you're dealing with, provided that the absolute values of the weights are bounded away from 1, let's say uniformly bounded away from 1, then you can actually show that this thing is a absolutely convergent sum, and you can think of it in that sense. So it's really a matter of taste how one prefers to view this. And one can think of identities of this form as being a very sort of far-reaching generalization of geometric series. Okay, so hopefully the statement is clear. But before I go to the proof, just a remark. So actually one may view this as computing an expectation or average of an observable, and the observable is basically this thing here, with this function g of mu that's valued on the random variable in question. That's going to be the thing that we're averaging. So one can view this as an average of that g of mu with respect to this probability measure here. Okay. So of course that that then raises a lot of interesting questions. If you actually want to say something about what's going on with this distribution of mu, if you make appropriate choices for this observable, and you see you have a bit of freedom here, you have a alphabet of variables that you can choose to be whatever you want. So under appropriate choices, you can see how this can potentially give you very important information about the distribution that you actually care about. Okay. So let's have a look at the proof. So the proof is going to make use purely of the Yang-Baxter equation. So I'll have have the following lattice. So basically what I'm going to do is first represent the left-hand side as a partition function. So let's maybe just zoom out a little bit and then do that here. So maybe I won't draw so many lines.
Excuse me?
Yes?
So can I ask you about the proposition 1? So what is the size of mu and nu? In that case, maybe I misunderstand, but is the size of x and z, are there the different?
That's correct. Yeah. So
You see.
basically the size of this alphabet
Yes.
has nothing to do with anything. So this is completely independent of everything else, all right? But
Yeah.
the size of this alphabet here, n, that's exactly the size of mu and nu. So mu is just mu1 up to mu n.
I see.
And
So mu and nu has the same size as n.
that's correct.
I see. Only x is different.
X is free. You can take whatever you want.
Thank you very much.
I have a question too. Can you interpret this identity as an eigenvector equation? Or
Yes, it's a very good question. So indeed, it does have such an interpretation. And so basically, what we're going to see, not in the lecture today, but tomorrow, indeed you can view this as a kind of eigenvector equation for the, let's say for capital G. And so one thing that one might ask for is, can you actually find a spectral decomposition of G in terms of this family in terms of this eigenbasis? And one of the things we're going to see is you can actually write a ultimately integral formula for G, which will involve precisely the F mu and G nu with some appropriate extra factors in here. So yes, the answer to the question is yes. Okay. All right, so here is a proof. Okay, so I'll start off with just this. And maybe I'll make a copy of that now. All right, so in the first step, let's try to set up our lattice so that it's actually computing that left-hand side. Okay, so at the bottom of the lattice, I essentially want that thing to compute for me the capital G. So I will make the choice, this is x1 up to xm here. And I will choose the boundary conditions here to all be zeros. And I'll have then the string, what was called T before, T1, T2. This is the string associated to nu. And then in the middle, I have to perform a sum. So there's a sum over, let's say, the string S in the middle, which is S1, S2, and so on. So this bottom piece, hopefully you can agree, this is nothing but G mu nu in this alphabet x1 up to xm. And likewise, at the top, I'm going to have something similar. So these variables, in terms of our conventions, they should be Q inverse Z1 inverse all the way up to Q inverse Zn inverse. And I will choose the colors that go out here to be of the form 1 all the way up to n. And notice that that conservation is being respected. in this partition function. Why is it being respected? Well, the string t at the bottom, each of the colors 1 through n is represented exactly once at the base of the lattice. So it should be that there is exactly one copy of each of them leaving the lattice, and that is indeed true. Okay. So the first step is to somehow turn this into something that looks like Yang-Baxter equation. And there's kind of trick here, which actually relates to the question earlier about stochasticity. So what we're going to do is attach a lattice here at this edge. So I'm just going to draw it, and then I'm going to claim that it's equal to the original object. Okay, so you still have all of your vertical lines, and let's continue to put the states. So it looks like this, and all of these are zeros. Okay, but for this extra piece that we've now added, I'll choose it such that everything entering it and leaving it is all zeros. Oh, sorry, I've a little bit too fast there. So these should still be T1, T2, and so on. All right, so let's think a little bit about what's happening here. So I have some colors entering from below. Let's maybe focus just on color number 1. So color 1 enters somewhere from below, and then it's going to start to move through the lattice to some point, and then eventually it's going to backtrack and exit once it gets into the top half of the lattice. So, something like this should be happening. But you can see that with this extra piece that we've now added here, there is a potential that maybe one of those paths can enter and actually head all the way out to here, and then head through this piece, and then at some point backtrack. So we have to worry about whether this will actually happen. And the point is that we claim that such configurations basically happen with probability 0. And the rationale behind that is very similar to before. So one considers, first of all, the statement on a finite lattice. So let's say T1 up to TP. And one then looks at the situation that a path has actually made its way all the way to the right edge. Well, in order to do that, it has to take many steps to the right. And in the limit where p goes to infinity, all of these, you end up with basically infinitely many steps to the right, and that thing will have a vanishing weight. So using this kind of heuristic that can be made very precise, one can conclude that actually all of these edges here will have to be zeros. No colors can either enter this piece or leave it. And so that allows you to conclude that the thing that we've drawn here is actually equivalent to the original one. All right. So once we've done that, then it's quite simple. So then you use the Yang-Baxter equation, and basically to drag the cross that we've inserted at the right, and start to push it all the way through to the left. And so the end result of doing that is this. All right. And so here I have conditions 1 through to n here, and these are still zeros. And in terms of the rest of the lattice, this is still T1, T2, etc., and these are still all zeros. And so now the argument concludes with the following observation. So this top half of the lattice, it actually has only zeros exiting along both the top and along the right. which means actually that all of these, everything that enters it will also have to be zeros. So all of these will get forced to be zeros. And so now you have a look at this piece. And so this piece is now quite interesting, because I have the colors 1 through n exiting, and the only possible place that they can enter that is actually in this way, so 1 through to n. There's no other way for this thing to be non-vanishing, if you think about it carefully. And so what I end up with is this frozen piece here, which I can maybe call pi. And so pi is going to be a function of the x's and also of the z's. And then this bottom piece, we've seen that function before. That's nothing but g nu in the variables z1 up to zn. So up to the weight of this piece here, I get g nu z1 up to zn. And if you go ahead and actually work out the weight of this frozen region, which is very easy to do because all of the vertices have the same form. So in this region, all of the vertices are of this form. So basically a 0 goes horizontal, and one of the colors, let's say K, goes vertical. And the spectral parameters that you have are, so this is going to be an X, and this will be a Q inverse, Z inverse. So the weight of that vertex is of the form Q1 minus Q inverse, Z inverse, X inverse over 1 minus Q times Q inverse, Z inverse, X inverse. And that thing simplifies to give you 1 minus Q xz over 1 minus xz. So you can see that basically you get such a factor, and that's exactly the factor that we're supposed to get on the right-hand side here. Okay, so that's basically how the proof goes.
I'm a bit confused. So could you go back to the first crosses that you added, the figure after this one?
Yeah, just here.
Yeah, this one. So when you added all these extra arrows ending with 0 and beginning with zeros, does that? So I'm confused about why you drew this brown broth, because I mean, wouldn't that force all of the things to be 0 anyway? I mean, because you have this conservation condition, right? That the 0. If I start from the rightmost thing where you have an arrow, I don't see why the brown thing would happen.
The one that I just deleted, right?
Yes, yes.
Yeah. So initially, what we have is this. So I don't have zeros here initially. So I want to come up with a rationale that says that those edges must be 0. All right. So the only way that they would not be 0 is that a path began somewhere in here, made its way into this region, and then exited. But that's the only way that they're not all 0.
But can that even happen at the because
in finite size it can definitely happen. In finite size it can definitely happen. There's absolutely nothing that stops that happening. Like suppose, for example, this red is a 2. So I have a 2 that
so it's not that 2 0. Oh, sorry, okay. So my confusion was that 2 zeros are entering, but it's not. It's 1 0 entering, and at each vertex there's 1 0 entering and 1 0 leaving. And so
that's correct.
Right. Okay, sorry. Yeah, I got confused about that point. Okay, and could you please explain argument in the next figure again? I sort of missed some of the points. So now I understand why the zeros are there in the top right in yellow, maybe whatever
Yes.
color it is, because of conservation, right?
Yes, that's correct.
Then where did you, how did you argue that you get 1 through n in that order?
Okay, so let's delete these.
Yeah.
Okay, so maybe let's begin with the 1. All right. So I have a 1 that exits in this column. And if I look at what comes into that column, so these are all zeros here. Okay, so I have a 1 that's going out here, but everything that enters that column, at least all of these edges, these are all zeros. So the only possible place this 1 can come from is here. Otherwise, there's no way I can have a 1 exiting here. Maybe that's, I draw the actual orientation of all of the lines. Right? So these are all zeros. So the 1 has to have come from here.
But couldn't the 1 go to the right and then come back?
No, because the flow is, yeah, it's difficult to, the flow is like this, right? So it's always heading up towards the northeast.
Oh, I see.
So it cannot backtrack. Yeah.
Okay, I see. Yeah. And then these extra these extra vertices which contribute to the product, they come from that m by n piece, right? That was the last thing you were showing. These.
That's correct. Yeah. This pi that I've written here.
Yeah.
Is precisely capital M times n factors.
Yeah.
And all of them have the form of this vertex.
Okay. Thank you.
Yeah. So I see that yeah, I've probably already had the 1 hour that was allocated. Yeah, I kind of didn't quite get through everything I would have wanted to do today, but I think it will be fine to continue, basically continue next time. So yeah, maybe it's a good point to stop.
Let's thank Michael. We have some time for questions. I have asked a lot, yeah, but maybe others, I should give others a chance.
Are there analogous relations that involve F?
Just, you mean, say little f and little g?
Yeah, like eigenvector conditions or summation rules or...
Yeah, so I was going to come to that. So seeing as you asked, it's a good opportunity to give the other identity. So I forget what proposition this is, maybe proposition number 2. Yeah, so the functions f mu and g mu satisfy the following identity. So again, I sum over all strict compositions mu. I have f mu. So here, all of the compositions have length n, as usual. Well, actually, there is only one composition showing up. So, well, there is f, and then there'll be something I call g star. So g star is just going to be equal to g up to a constant. So g star mu in z1 up to zn. And this one is equal to something slightly different. So I have product from I equals 1 up to n, 1 minus xi, zi, and then a second product. But this one is of a triangular form. So it's over all I greater than j. And 1 minus q xi zj over 1 minus xi zj. Okay, so it's kind of similar to a usual Cauchy type product, but some of the factors are missing. And here G star mu is defined to be G mu times a factor, which is just Q to the n times n plus 1 over 2 over Q minus 1 to the n. So just as some Q factor that multiplies to give G star. And this identity, this is not really so much like a Cauchy identity. So I really want to say that the one that we proved is very similar in spirit to what's called a skew Cauchy identity in the theory of symmetric functions. This one is a bit different, and this is more closely related to. So there's a paper by Mimachi and Naomi. I forget the year, but basically they prove Cauchy type summation identities. For non-symmetric McDonald's. And so this type of identity here is very much in the spirit of what they did. So there is a way of actually matching these functions. So at the moment, these are some multivariate rational functions in these n variables. But one can actually consider slightly more general model, so a fused model. And in the fused model, there is a way to actually convert these things into polynomials instead of rational functions. And the polynomials that one gets are nothing but the non-symmetric whole-Lederer polynomials, which are in turn special case of the non-symmetric McDonald's. So I just want to say that all of this lives on the same tree as what they considered. Yeah. Hopefully that answers the question.
I have one more question. So in all of these identities, you always, I mean, in this whole setup, Q is always fixed, a fixed parameter, right?
That's correct.
Is there any limit in which you get the original Cauchy identity using Schur polynomials?
Oh, you mean just the standard?
Yeah, some S mu, S nu. Yeah.
Just this?
Yeah. Product 1 minus xyz.
Yeah. So that's kind of related to the comment that I was making here. So if one goes to the to this type of, so this is more like a true Cauchy identity.
Yeah.
So yeah, there is a version of this involving not G's actually, but let's say a capital G times what we can call capital F. So there is such a identity, and that identity again has a lift to this kind of fused world, this fused vertex weights. And once one works with the fused vertex weights, there is indeed a limit that takes you to whole Littlewood polynomials, and then from the whole Littlewood polynomials, you can get down to Schur. So there is a way to get to Schur, but one has to go higher up before you can go down.
I see.
But if that makes sense, yeah.
Yeah,
I should
yeah.
say that it is possible in all this business to take Q to 0. So just with what we're working with, you can take Q to 0. But if one does that, one does not get Schur polynomials, one gets actually Grothendieck polynomials. So Grothendieck polynomials are sort of underlying the Q equals 0 degeneration of the model.
I see. I mean, here also the problem is that your F mu and G mu are not symmetric, right? They are so directly getting Cauchy would have been.
Yeah. So here the G's are not symmetric.
Yeah.
The little g's are not symmetric, but the capital G is.
Yes. Okay. If there are no further questions, let's thank Michael again. Thanks, Michael. So I guess we'll see you tomorrow.
Thank you. Yeah, it sounds good. Yeah.
Okay. Bye.